Yeah, every week for Alex.
Like here.
No. Some people have it because they like to use the text. Okay, or at least as far as I know, that's why they've got it. I hope they're not using it for a calculator. Okay, what you're supposed to do on this is obviously score each problem. If you have a problem that's wrong, draw a hash mark through the problem number. Then hopefully with a contrasting writing color, write what the correct answer should have been. Then, after you're finished grading all four sheets, all four parts of this, add up the total number you had correct. I'm not going to tell you how many total there were, although you can probably figure it out if you want to. Now, add them up, get the total number correct. Then I want you to put that total number at the top of the addition page near your name with a circle around the number. Evening. Sure. 7:05. You're not late. As hot as it is in here, I'm just letting you guys do something that's productive. Okay, those of you who just came in, go ahead and start grading this multiplication sheet. After we finish all four pages, count up the total number of answers off of all four pieces and add them together and put it up close to your name in the addition page and circle it. By the way, for your name, everything is always last first, hopefully printed, so I can read it. Because that's also the way I do grade book entry, is everything is alphabetical by last name. Now, by online class, I need this page and the other pages available to them online because they're not required to watch these videos. They're in the course materials section of your Blackboard.
I noticed that.
Well, hopefully they'll help. Give you a second look at stuff if you have a question. Yes. You guys don't have access to it. That's just the online class. Because they're not required to watch the video. Although it's recommended. If they watch it live, you know, that's fine. If they want to watch it later, then they have to wait till probably sometime after 11 o'clock when I get it on YouTube. Okay, for the student who just came in online, the two students, here is the multiplication page. You should have also gotten an email that I posted these answers in the course materials block of Blackboard. And that's for the online only, not you guys. You see, they're gonna have to email this into, whereas you guys just handed in to me tonight. Okay, we're officially started now. And so I'll give my instructions for about the 5th time. Grade all of it. At the end, by the way, with a separate color marker, I suggest you write the correct answers to any that you missed. Count the total number of answers you got correct and put it in the top of the addition page and circle it. And also be sure you got your last name, first name on the addition page. And then I'll have you turn them in a few minutes.
You want to also write in person AL04.
You don't need to on this.
The number 22-Wk2.1-Gd39-40.
29.
Yes, at the bottom, the word from.
Oh. Well, let's see. Should be 3.
Okay.
7 times 9, 63. So if I take 9 times 7, I'm gonna have a 3 there.
Okay, because I couldn't tell if it was a 1.
Yeah, understood. It's a scribble either way. How many are not finished with this one? Anyone? Okay, we can go on to the next page then. The division page.
I was looking at the subtraction page. I'm like,
Freak yourself out. Did you?
yeah. I was like, what? How did I get this?
By the way, the answer on 29 is negative $60. You lost $60. I tried to increase the size of this as much as I could to make it easier to read. Then on 27 and 28, you can see the steps involved in getting the answer. Now, if you had -4.5, and if you had +3 3/4, you do need to change those to improper reviews. Because that's the format we submit answers in algebra. The other way is grade school math. Okay, as soon as you have all of your years graded and you've added up the total and put it up at the top, please lay it right here. And as you pass my camera, really try not to bump it. You did.
I was gonna be slow.
Yeah. Pages. Okay, distance, rate, time. D = RT. Phonetically spelled dirty. Okay, now, what is distance, rate, time? It's the formula that tells you how fast you gotta go to get somewhere in the time you wanna make it. Okay? For example, if I drove to Denver 500 miles, that's a fixed number. Now, if I drive 50 miles an hour, average, and somewhere along there, you're gonna make a stop for gas or ungas. Now, but if you drive 50 mile an hour average, yeah, think about that a bit. It's gonna take you 10 hours to get there. $500 equals 50. That's a 50 times however much time it is. We divide both sides by 50. And we get T, or the time to get there, 10 hours. And we have to label it, of course. Now, likewise, with this problem, what if I said I want to get there in 7 hours? How fast do I have to average? Now, keep in mind when I say how fast you have to average, you got to really drive faster than that to compensate for your brakes when you're going 0 miles an hour. Okay? So we take that 500 miles and we don't know the speed, but we know that we want 7 hours. I could have at least picked a number to divide nicely. So I'm going to divide by 7, divide by 7. Strange looking 7. So 7 goes into 50 7 times, that's 49. 1 remainder, 7 goes into 10 once. And In this case, 3 remainder, and it's going to actually be 71.2 miles per hour. We're taking miles dividing by hours. That's what MPH means. Okay? So, you see, we can use this formula in different ways. Now, what if I drive 6 hours at 80 miles an hour? How far will I go? Well, in that case, 6 times 848, so it'll be 480 will be the distance that you travel. This would be miles in 6 hours at 80 miles an hour. So that's 3 different ways you could use this formula, okay? Now, given that information, let's solve this problem. Or that background, I should say. Okay, a hiker can hike 1 mile an hour faster downhill to the lake than she can uphill to the campsite. Well, you know what? That kind of makes sense, doesn't it? You're going to go downhill faster and you're going to go uphill, or at least for me. Now, if it takes her 3 hours to go to the lake and 4.5 hours to go back, this is saying 3 hours down, 4.5 up, okay? What's her speed going back to the campsite? Doesn't tell us how far it is, does it? But we do have basically this formula. We have the distance, whatever it is whatever the rate is times 3 hours. Okay. She can go downhill. So this is the rate plus 1. Why? Because it says she can go 1 faster. We also have the formula D equals the rate times 4.5 hours. Okay. The distance is the same. So that means that this stuff is equal to that stuff, since the distance is the same. So R plus 1 times 3 equals 4.5 R. That's your formula to solve this problem. R will be the speed going, in this case, downhill or uphill, and this will be the speed going downhill. Okay, our variable is the one they didn't tell us anything about. They didn't tell us anything about the speed downhill. They did tell us, uphill, I used the wrong word, I'm sorry. They did tell us something about the speed downhill. It was 1 mile an hour faster. Okay, so that goes back to those rules that I was telling you before about how you structure your problem, and then you go ahead and solve it. Now, I'm giving you this fundamental right here. I'm going to erase it and just show you their solution, which includes everything that I've put up here. And we'll just go that way. They like to make tables. I don't make tables very often. You saw how I did it right here. But they decided, here's the rate downhill. Here is the time downhill. Here is the rate uphill. Here is the time uphill. They're both equal to whatever the distance is. So fundamentally, they've said the same thing I did, didn't they? Okay, well, if you take this times this, rate times time, that gives you the algebraic distance. And here, Rate times time gives you this. These two have to be equal to each other. Okay? So this distance has to be the same as that distance. They're both, however, the same miles. And then there's the problem that you saw that we were ready to do over there. Now, here's the actual solution. Distribute. Get all the variables on one side by adding -3x both sides. Divide both sides by 1.5, so you get 1x. I used R. Hey, I used R. Why did I use R? Am I trying to be a pirate? Or unintended. I'm just trying to fit the variables to the problem. That's what I'm trying to do. And to me, it makes more sense to use R's instead of X's on this. Okay, but that's just me. So I divide both sides by 1.5, and I get the distance is 2 miles. And then we can check it. So we've got the 2 miles and 2 miles per hour rate. You do have to label that. The distance isn't 2 miles, the speed is 2 miles per hour, which for going downhill, actually, that's kind of slow, which would be 3 downhill. 3 would be the downhill, and 2 would be the uphill. But the 2, yeah, 3 downhill seems kind of slow to even me on these old things. I used to be a pretty good hiker. I took a group of 15 high school kids while I was on active duty in the Army on a 10-day hike, totally self-contained. We packed everything we had along the Appalachian Trail from West Virginia to Northern Virginia. That was one of the highlights of my life. Okay, we talked about literal equations. Now let's talk about geometry. We're going to be dealing with rectangles and squares and all that stuff. Look in your packet, almost at the back, somewhere around maybe page 28, 29, 30, somewhere around there in your packet. Anyone not have a packet with you tonight? Well, that's one, but that's not actually the one I want. This is the one I want. It's page 24. And actually, there are 3 pages there together that have a whole bunch of math formulas in it. But that page in particular is geometry. A lot of times this book assumes you know those formulas. And maybe you do, maybe you don't. Okay, so anyway, I've provided them for you. All right, so the length of a rectangular corral is 2 more than 3 times the width. Now, if I see this problem, I start drawing a picture. Rectangular. The length is 2 more than 3 times. We did some writing exercises like that, didn't we? Than the width. Okay, and actually this could be a W also. 2 more than 3 times the width. We don't know anything about the width. Now let's see what else does it say. The corral is situated so that one of its shorter sides is adjacent to a barn. That's the barn, looking down from on top. Okay, one of those roofs that goes up, and then over some more, and then over some more, old style barn. Okay, so this is what we're talking about. So they don't really have fence because they got a building. Now, what else does it say in here? Yeah, this part doesn't require fencing. Right there, it says that. If the total amount of fencing is 774 feet, what are the dimensions? That means from here around to there is 774 feet. Okay? Now, the formula we're going to use is the formula for perimeter. Okay, everyone found that in your packet? Okay, it should look something like this. As soon as I get this, what I've read in erasing very well tonight. Okay, for perimeter, you've got 2 times the length plus 2 times the width. Now that's the general formula. Now let's see where our picture fits into this. Okay, we got 2 lengths, this one and this one. So I've got 2 times 3W plus 2. Okay. But I've only got 1 length instead of 2 lengths. So plus W. Only 1 length or width. Okay, so there's my formula, and they tell me that this is 774. We have just written the formula to solve this problem. Did you see the procedure? How I analyze that? I'm basically trying to model to you how you think through these problems, okay? Because I know that word problem solving is hard for some, or has been. Well, now we just got to solve this thing. So 774 equals 6W plus 4 plus W. 774 equals 7W plus 4. Okay, I'm going to take, I think I'll take this 4 over there. Minus 4 minus 4. So I get 770 equals 7W. Divide both sides by 7. And it goes 110 feet is the width. Question? Okay, so if that's the width, what's the length now? Well, we got to take 110 times 3 plus 2. So that's 300 plus 2, what? Oh, thank you. Wonder time, right? Okay, so 330 feet plus 2, or 332 feet is the length. Question about how you do that? Yes.
So just to clarify, you just took the answer from W and the W plus 2.
Because this is a comparative length. So we take that length and substitute it in. Okay. Can I erase? Okay. Well, Here's their work. Looks prettier, but kind of like my drawing. Okay. So they're saying the distance around the three sides is 2 times that length plus 1 times that width, which is basically what we did. That's exactly the same formula we had. And then they went on to solve it and got exactly what we did, thanks to someone catching my error. Okay? And then you have to label your answer. Always. We're going to skip this one and that one and that one and that one. These were all slides that I used in another class that met several days a week. And now we're going to go into linear equalities, inequalities in one variable. Okay, we all know that linear means straight lines, right? Okay, what are inequalities? That means less than or equal, greater than or equal, etc. Okay, so let's work with that. I'll let you just read that. I don't know that it's worth writing down, but please do read it. Again, these symbols constitute the verb, just like an equal sign would. Now, see these 4 symbols. I've got to tell you a story to give you kind of an idea of what those symbols really mean. Okay? Now, for some reason, my wife, who is a very brilliant person, 47-year teacher, not years old, taught that long. She's saying that actually she's 5 days older than I am. I married a younger woman. But anyway, she, for some reason, the concept of less than or greater than was difficult for her. I guess her grade school teacher talked about alligators and all kinds of weird little stuff like that. Well, let's keep it simple. The KISS factor. Keep it simple, silly. Now, what this one means is that means the littler number goes on this side, the bigger number goes on that side. That's what it means. Now, what's littler and bigger? On a number line, you start with the negative values on the left and you work up to 0, and then you go to increasing positives. It's just like the AD-BC timeline, where in BC they counted backwards towards 0, and then AD from 0. Okay. Oh, by the way, speaking of that, now here's another little aside. Remember we saw the weird number, and we talked about the number sets, the whole numbers, the natural numbers, you know, the rational numbers, the rationals came into, and then there were these other weird numbers. Okay. Well, the difference in whole numbers and natural numbers is whole numbers are just counting numbers. They have no 0. And I just said that backwards. Natural numbers have no zeros. Whole numbers include the concept of 0. Now you might think, how can this be? What can be a set of numbers with no zeros? Think Roman numerals. I, IV, V. That's 5. VI, VII, VII, IX, and X. So as they approached every 10, they had to generate a new letter of the alphabet. Okay, and then you have XX for 20 and XXX for 20 for 30, and IL for 50, or for 40 rather. XL, 10 subtracted from 50. And then you had L for 50, and then you go up to XC, which is 10 less than 100. C is 100. Ever hear of a C note in a gangster movie? $100 bill? Ever hear of a centipede? Cent, C, centimeter? It all means 100. Ever hear of a centurion? The Roman soldier in charge of 100 soldiers? Okay, it all fits. And they had this kind of a number system. Now, oddly enough, do I have any Hispanic students in here? Be proud. Be proud. In the 1200s, plus or minus a few years, in two places in the world, opposite polar-wise, and I'm talking the Middle East, and I'm talking the Mayans, okay? The same discovery was made by both civilizations at about the same time. Furthermore, both of those civilizations built pyramids. I'm talking Egyptians and Mayans. And both of them, ironically, at about the same time on opposite sides of the world, back before Columbus, because he wasn't until 1492, and I'm talking 1200 something, they discovered the concept of zero and they used it in their calculations. And that was the amazing, one of the most profound turnarounds in mathematical thought that has ever existed. Virtually none of our present mathematics would work without that concept. Okay? Now, I said I was going to digress, but hopefully, you know, they say college is to make you a little broader knowledge. So maybe that's a little piece of broader knowledge. Okay? Now, back to these. To the left are negative numbers approaching zero. And then to the right is bigger numbers. All this means is that whatever number on this side has to be littler than that number, meaning farther left on the number line. Likewise, this one means whatever's on this side has to be bigger than whatever's on that side of the number line. This one means it could be littler or it could be equal. And likewise this. Now, I want to give you another story. This is a story of my youth. I'm not going to call this a true story, but some of you might notice a certain passion with which I'm going to tell it. When I was growing up, teenagers didn't have nice cars, unless your daddy was a doctor. We had clunkers that we had to keep running, and we had to fix flaps on, and we had to fix this and that to keep them running. A number of people would buy used parts from the junkyard in order to save expense, and so did I. But some people decided to use what they call the midnight auto salvage.
Oh, no, it's not.
You know, they procure their parts at a significant discount
It's called acquisition.
at night. Yeah, acquisition, whatever. We used to do some of that in the Army too, but that's a whole different story to cover our losses.
It's a requisition.
Now, no, you didn't put it in requisition. You did it.
Yeah, it's an unofficial requisition.
Now, I got to keep going. Now, when you excuse me, when they approached the junkyards are almost always covered with a chain link fence. Big, tall one, hopefully to keep people out. And to varying degrees, it was successful. Well, when just the fence wasn't enough to keep people out, then they started putting an animal in there at night. During the day, they keep this animal chained with a chain about this big around. Steel, hardened chain. And at night, they would let this junkyard dog roam freely. And that junkyard dog's whole mission in life was to intercept and attack anybody that tried midnight auto salvage. And you're by now thinking, what the heck has that got to do with less than or greater? Well, here it comes. After a while, some of the guys got kind of tricky and they would create a diversion or throw a hunk of meat over the fence to divert the dog. So the junkyard started electrifying their fence. You ever touched an electric fence? You don't want to do it twice. You don't want to do it twice. Okay, that's where these come in. Okay, these two they never actually include if 3 is less than 4. That's an absolute statement. Okay. Now, if 3 is less than or equal to 4, the 3 could be included. Now, what's that got to do with the fence? If the fence were electrified, you would not want to touch it. You could come just as close as you could, but you wouldn't want to touch it. You wouldn't want to become part of that. Now, usually these symbols are used something in the sense like 2 is less than, X is less than 3. In other words, X is some number between those, some amount between those. If it's electrified, okay, you don't want 2 to touch it. There's going to be a gap here where 2.5 is. It'll be more obvious to you if I put 1 right here. What number is missing? 2. Okay? 2 does not exist that you can touch, that you can graph. You can graph 1. You can graph 1.999. You can graph 3. You can graph 2.000001, but you can't graph 2. Now, that's like an electrified fence. You can't touch that electric fence. An old junkyard dog knows that too, because he ain't going to touch his nose to that. Okay, he's too smart for that. But what about if I throw an R equal in here? Then that means the fence itself is inclusive. It would include the value of 2. It would include the fence. Now, anyone ever put their fingers through a fence? You do that with an inclusive, non-electrified fence, and junkyard dog's are going to have a hunk of your fingers in his mouth. Okay? So R equal means it's inclusive. You get in the plane of that fence, and so does the dog's mouth. This, without these, means it's an electrified fence. You can ride up to it, but never quite touch it. It's always smaller. away. Okay, and that's what these really mean. Okay, it gets close, but it will never touch. If you have the R equals, then it can touch and include. So you're going to hear me using the words points inclusive. And that's what I'm going to be talking about as we go on. Now, I've taken 10 minutes to talk about this a little bit, but experience has taught me that this is sometimes kind of a hard concept for people to really understand. But it's that idea, you can't come up there and put your fingers in the fence. Okay, if it's just less than or equal. Doesn't include it. Okay, so anyway, here we go. We're going to solve some things. You can read that one. All this is saying is if this statement, if you add C to both sides, you haven't changed the truth of things. Here, it's going to say if you multiply A and B by C on both sides, it's not going to change. That's the same rules we've had for equations, isn't it? As long as you do the same thing to both sides, you're okay. Now, there are two differences in dealing with inequalities. You're going to solve an inequality just like you solve an equation with two differences. If you multiply both sides by a negative number, a positive doesn't matter. But if you multiply both sides by a negative number, then it will switch the direction of the symbol. Likewise, if you divide both sides of an inequality by a negative, then it will switch the symbol, whether it's going this way or that way. Let's see why. Agreed? Okay. If I take positive 2 times both sides of this thing, I get 6 is greater than 4. Still true. What if I take negative 2 times both sides? Negative 2 times 3 is negative 6. Negative 2 times negative, or 2 times negative 4 is negative 4. Now, to make this a truth, which number is closer to the 0 on the number line? That one is, isn't it? So it is now the greater number. And likewise, division is the same way. If I have 3 is greater than 2, but, well, let's don't even go that way. Let's say 4 divided by 5 is 0.8. Is that true? Yeah. Okay. What if I multiply or I divide? I'm going to change this problem. Start all over. Okay. I've got my 3 greater than 2. I'll stick with that example again. This time, what if I divide both sides by the same negative number of -5? Well, here I get -3/5. Here I get -2/5. Now, which one is now greater? This one is. So that's examples of why, if you multiply or divide both sides by a negative, then you have to flip symbol. Otherwise, solving inequalities is the same as solving equations. You know, you add the same thing to both sides, you separate the variables and the numbers, and all of those kind of steps. So this is just telling you what I just told you. except it's the rule format. Okay. Once again. Here's just a little explanation. Again, this is inclusive. Now look at this symbolism. In high school, you may have used dots and closed dots and open dots. Okay, we don't use those anymore. Well, just let me warn you, in college algebra, this is what will be used instead of closed and open circles.
For the
Okay.
classroom, that's what you want to use. Yeah.
To prepare for college algebra, get used to this, especially when we do something called interval notation. Now, this symbol is the equivalent of an open dot showing all points that way are included. Okay, this is numbers less than or equal inclusive of 3. You can put your fingers in that. This one, on the other hand, is a non-inclusive symbol. All of these are real points that could be part of the answer, but not 3 itself. Okay? Because that's that electrified things that you can't actually touch 3. That's what this symbol represents, same as an open dot. Okay. Again, inclusive, exclusive. For some reason, my glasses keep sliding down my nose today. It's irritating. Okay, this is called interval notation. This is the way most of your answers are going to be required. This way is called set notation or set builder notation. Now, up to this point, you probably just use this. Let's translate this. The set of x values that behave in the manner, but we use the word such that. There's the rule. Here's what we're setting, and here's the rule for that set. That whatever it is, it has to be smaller than 3, or 3 itself, is what that means. This, the set of x values, where x is less than 3, but not inclusive of 3. Set of x values where x is bigger than 3, but including 3. And likewise, not including 3. Now, what does this interval notation mean? You notice it uses the brackets and parentheses. Let's look at this. We always read graphs left to right, just like we would an English notebook. Okay? This goes all the way to negative infinity. Okay? That's what that arrow represents. But it has a stopping point, an inclusive stopping point at 3. In interval notation, again, we read left to right. We start at negative infinity. And infinity is always a non-inclusive because you can never find infinity. There's always one more, and one more, and one more. Okay? But it goes from wherever negative infinity is all the way back to 3 inclusive. You see how the graph looks identical to the interval notation. Here, only difference is we're not including the 3. Here, going left to right, we start at an inclusive 3 and we go for never. Okay, because it never ends. Here, we do not include the 3, but it's everything 3.0000000 and so on 1 forever. Okay, so that's the concept. This is going to be our standard answer format. It will vary in Alex. Okay, back and forth.
So is the inclusive the closed circle?
Inclusive is the equivalent to closed circle. Okay, and that's the brackets. Exclusive would be the parentheses or open circle.
And so infinity will always have the parentheses.
Infinity will always have parentheses because it's never determinable. Hard word for me to say. Okay, let's work this problem. We worked problems like this one before, except we didn't have the inequality. Well, we got to do the distribution first. Does that sound familiar? Yeah. Okay. Now we combine like terms. That sounds kind of familiar. Now we've got to put numbers on one side and variables on the other. Okay, so I move this 2x over here. All right. Now, adding or subtracting does not flip symbol. Multiplying or dividing flips. Okay, that's a biggie. Don't accidentally flip when you're adding a negative. It's only when you multiply or divide a negative. So anyway, we simplify again. These two make x. Here's the 7 and there's the -9. Now we're going to move this 9 over there. And when we do that, we get x is greater than -2. Now, there's the graph of this. There is no inclusive. So -2 on the graph. Now, I would want you to always show for me the relative position of 0 on your graph. Okay? I always want you to show me where 0 is. These two items would be considered labeling your graph. You don't label them, you don't get points. It's that simple. So here would be the graph of this equation. Now, what would the interval notation look like on this one? Well, interval notation would look like this: to positive infinity, like that. That would be the interval notation. What would the set notation look like? Set of x values such that x is greater than -2. You look a little puzzled. What?
Let's do the ones that.
These are just set brackets. Your answer is stuff made up of what's inside it. You got points here. This is actually a point there. Here's -1. Here's 0. Here's +1. Here's +2, +3, +4, +5, and to infinity. So this is saying we've got a set of x values that begin at -2 and go that way forever. Okay. Now, here's a nice thing about it. Here's a graphing hint for you. Okay. When you have the variables on the left, because this is an equally true answer. That's an equally true answer to that. But when you have the variables on the left with inequalities, look at the direction of this symbol and look at the direction of my arrow. It will always do that. Always. So that's a major graphic help. Okay. Now, you notice the symbol on these two is flipped. I said if you multiply or divide by a negative, it flips symbol. There's one more change. If you do what's called the reflective or reflexive property, like a reflection in a mirror. Everything left is right, everything right is left. If you do that, if you completely flip sides, then you must also flip symbol. Okay, so those are the two big differences. You multiply or divide by a negative, or if you flip sides, reflex. Okay,
So with inequalities, do you want us to always graph it?
if the instructions say so, you darn sure bet. Now, if the instructions don't say so, and the instructions said, put your answer in interval notation, simply looking at this is going to make interval notation easy to write. So sometimes it's a useful tool, even though the problem doesn't require it. And I'm talking a rough sketch. Okay?
Do you always want the positive sign when it's asking infinity or do you just put infinity?
Usually I don't put the positive, but I did to make a point tonight. Okay? Can I erase? Well, they're just repeating what I already did. Okay, here's another one for us to solve. Any questions about solving that? What did I do? Well, I combined variables on one side, then I moved the numbers to the other side, then I divided both sides by 5. Same thing we would do if it were an equal sign, right? So now, here is the set notation for this, but here is the interval notation for this. Now, to go just from this statement to that statement might be a little bit confusing. But if you draw a number line, 11/5 is 2 1/5, right? And that's a positive. So out here's 1, here's 2, and here is 2 1/5. Okay. Now, what does this statement say? It says the x values that are true are all smaller than that number, lesser. And the direction arrow verifies that it's in the lesser direction. So how would we graph this now? Well, because there's no equal, we use a parentheses and draw our arrow this way. Now, does that make this interval notation make more sense? To me, it does. Because it basically gives you a groundwork to do it from. Well, let's do, actually, they did graph. Except theirs is prettier than mine. Okay, here's the next problem. Same kind of steps. We've got an or equal this time. Okay. Well, we got all the variables on one side. Now we're going to get all the numbers on the other side. Now we're going to, whoops. We're going to divide by a negative. So what's that going to do to this symbol? It's going to flip it. So it did. And here's where you show the difference. Okay. Now, if I were you doing this on a piece of scrap paper, when I showed divide by -17, divided by -17, I would also overwrite that right there. That's just the way I do it. So I don't forget to do it later. Okay, so there's our two answers, and there is our graph. So x is smaller than 1. That means the arrow is going to be going this way. Or equal. So we use a brackets to show equality or inclusiveness. And then the arrow going for an ever. Question? Okay. Here's another one. I'm just going through the same set of steps. Now we're dividing by a -2 on both sides. So we're going to have the flip symbol. And we get this. Okay. All this is fractions or decimals. Let me get this stuff out of the way. Just in fraction or decimal form. And again, fractions are generally preferred, but for graphing, sometimes you do have to change to that. So there's my graph. What's wrong with this graph according to the standards of Mr. Carter? I have not labeled where 0 is. Where is 0? Well, this is -3.5, so 0 is somewhere over here. Okay. Is that precise measurement? No. It's a sketch. Okay. And then there's the set notation. And if you look at this, parentheses, -7/2 to infinity and beyond. Yes.
So for that -7/2, when we write it down, do you want to write it exactly like that or simplify it?
That is simplified. Reduced improper is considered simplified for algebra. Do not change to mixed numbers. The only time you would change to mixed numbers is maybe for graphing, that you would know that this is a -3.5. That's the only reason you would change that to mixed numbers. Okay.
So for set dollar notation, do you want the fraction or do you want the decimal?
Yes. One or the other,
Okay.
preferably the fraction.
So if you do the fraction.
Yeah.
Mhm.
Fractions are the preferred. Believe it or not, in this class, they're going to be easier. Yeah, it's easy to make mistakes in conversion. Unless you're wonderful in long division. You guys will really love it when you start dividing polynomials.
Oh, what now?
That's a different story for a different day. Okay, here we go. Here's another one. Just a little more complicated, same idea. We got some things to combine like terms. Now we got to separate the x's and the numbers. There I'm moving the x's over here to the left. I'm moving the numbers to the right. So I simplify it to that. Now I have to divide both sides by -4. What's that going to do? It's going to flip. Okay. So then there is my answer. 0 over anything is just 0. Okay. Something over 0 is undefined. Remember that from the other night? Okay, so here is my solution. Now let's look at my graph. Well, this is inclusive, so that means 0 is included in that. And the x value would include all of the points that are less on the graph. Well, this leads us to an easy interval notation because we're going to go from -infinity, and you do have to show the negatives, to 0 inclusive. Okay. Oh, that's kind of an ugly looking thing. Well, you know what the easiest way to do this? The easiest way to do this, put that over 1, least common denominator is 3. multiply -3, excuse me. -3 times -5x plus 2 greater than over 3, -3, greater than -3 times x plus 2 over 1. Okay. These two cancel each other out. So -5x plus 2 greater than or equal to -3x minus 6. Okay. Now, from there, you just solve it like we've done all of what?
So, and then there is we don't have, or we don't do like negative, we just leave that the same.
I took this common denominator of -3 and I multiplied it times every term. And remember, the fraction bar behaves also as a parentheses for grouping. So this is all grouped together as one term, and that's all grouped together as one term. I don't know if I've answered your question.
So, when you take the -3, are you multiplying that by -5x and then also?
I took, I didn't have to multiply this, I didn't have to distribute this one because it will cancel with that one.
Okay, so how much can you do, you don't have to do that.
Correct.
Okay, so I see on
You
the right
want
side.
it to cancel because you want all ones down here. Okay, because that gets rid of the fractions. Now, did I answer your
Yes.
question? Okay. And then you go on from there. Well, this is worked in the PowerPoint, so I'm going to erase this. But I wanted to show you how I would do it. They may possibly show us a slightly different set of work. Well, no, not really. That's the same thing I did. And I canceled this -3 and that 3. And then I distributed that.
You just not conflict with these columns and that.
Yes. Why did I have to flip the inequality? Because I'm multiplying by a negative on both sides. I did that, but I don't think I showed it or mentioned it before. By the way, you could do it this way and break that uncommon denominator, realize this thing, and make it this plus that and that, but there's no advantage to that whatsoever. It's just extra steps to make a mistake in. Okay, so anyway, we got rid of these 3's. We distributed that one. Now we're going to simplify like we've done before. We got all the x's on one side. We got all the numbers on the other side. We're going to divide by a -2, which will flip the symbol a second time. Okay. That will flip the symbol a second time. Will that always happen? No. It will sometimes happen. Okay, here's where we left off before, where we flip the symbol because we're dividing by negative on both sides, and we get x is greater than 4. Here's the graph. All numbers bigger than 4. What is my interval notation? Parentheses 4, comma, infinity, parentheses. By the way, if any of you want to bring a very small battery-powered electric fan and put it on your desk blowing on you, you have my blessings. It's a steam bath in here with this many people in here.
We're shooting before this, is pretty warm in there.
No, even when we came in, it was. Okay. Wordy problems. Remember, the less than or equal is the verb. Once again, Beth got grades of this, 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 and this. By the way, this problem is kind of how you can figure out what kind of a score you need to get on the final to get a whatever letter grade you want. Seriously. Except we've got some weightings, and we'll talk about weighted values later. In exam 3. But anyway, she has these 4 scores. To have an A in the course, she has to have a 90 or more. Just like my class. What score does she need on the 5th test to earn an A? Well, we know these 4, 97 plus 82. Average, just add them up and divide them by how many there are, right? Plus 89 plus 99 plus your unknown test score, divided by a total of 5 tests. Okay? Now, I'm going to erase that because I have work on the slide. But that's my thinking. Okay? Now, oh, you know what? I left something out. I left out the fact that all of this has to be greater than or equal to 90. Doesn't that make sense? If you got to have a 90 or better. So that's why it has to all be greater than 90. Glad I remembered that so I didn't feel silly when it came up here. Okay, there's your greater than or equal, because it can be 90. 90 point nothing. So there's fundamentally what I had on the board. Well, we're going to add them together, then we get 367 plus the x over 5 is that. We got to get rid of this 5. Multiply by 5 on both sides. Which gives me this. Now we're going to take this up to the top of the next page. Oh, we didn't. X is greater than or equal to 83. That means on that 5th test, you have to get at least an 83% in order to get an overall A course. Questions on this problem? You look a little puzzled.
So is 90 supposed to be X?
90 is your goal. In other words, to get an A, you've got to have a 90% overall. Your average of all your scores has to be bigger or equal to 90. That's where that 90 comes from. The X is just the score of your last test.
This is the overall equation saying that one deviation. So is that
The score you need to get, if you get an 83, we put an 83 right there, you will get exactly 90.0. If you get an 84, you'll get a 90 point something. If you got a 92, you'd probably have like a 94, 95. Okay, do you understand that? Okay. Compound inequalities.